Last week, we discussed about various ideas of how to turn text into numbers that computers can work with, and we ended on word-to-vec, where words are represented as vectors trained inside the intermediate layers of a neural network. But we still face a challenge. Let me show you by looking at these two sentences. Hi, I am Bob. Hi, my name is Alice. I like to eat ice cream. The first sentence has 4 words, the second has 12, which then a numerical representation would translate to 4 vectors and 12 vectors respectively. However, neural networks typically require fixed length inputs. So how do you handle these variable length sequences? This is where recurrent neural networks come in. They achieve this by introducing the concept of time steps, which I'll denote as T, where each word in the sequence corresponds to a specific time step. For example, in Hi, I am Bob, Hi is at time step equals 1, I at time step equals 2, and so on. Normally for a linear layer, when given some input vector x at a time step t, it'll propagate through the linear layer and get back an output vector, y at time step t. However, for an RNN, it keeps a copy of this y, t, as a hidden state, h, t. This hidden state is passed along to the next time step, where it's combined with the next input vector, x, t plus 1, to produce the next output, y, t plus 1. There are 2 common ways to combine the hidden state and the new input. One is summation. The hidden state and input vector goes through separate linear layers, and then their output is summed together element by element. The other is concatenation. The hidden state and input vector are concatenated and pass through a single linear layer. This y t plus 1 is then called h t plus 1, which then again we use together with the input of x t plus 2, and so on. In essence, this layer's outputs are being reused as inputs to combine with future inputs to create its future outputs, hence a recurrent neural network. So why is this recurrent behavior useful to neural networks to model language? Well, words are not isolated entities. They derive meaning from their context, and this hidden state allows the RNN to remember the previous input of words and use that as the context for performing some task. Like in our example, we would input hi's vector representation into the RNN first, let it go through this linear layer, and its output will be used as the hidden state alongside the next input word vector representation, I, and so on. Now, initially that context should be nothing, a hidden state vector of all zeros. But as we input one word to the next, the memory gets updated based on the new coming information and carried over to the next upcoming input. There are various types of language modeling tasks, one-to-one, one-to-many, many-to-one, and so on. Let's look at the many-to-one case. For example, given the sentence, "This movie is good." A recurrent neural network could input those words one after another and output a number to say whether the movie was perceived positively or negatively. In a many-to-many case, for instance, given this Italian sentence,
Sei molto affamata.
the network might translate it into another language, like English, as "you are very hungry." Andrew Cabarsi, formerly an OpenAI employee, wrote this in his blog post, The Unreasonable Effectiveness of Recurrent Neural Networks. As you might expect, the sequence regime of operations is much more powerful compared to fixed networks that are doomed from the get-go by a fixed number of computational steps, and hence also much more appealing for those of us who aspire to build more intelligent systems. Well, while RNNs are powerful, they have a bottleneck problem. Their memory is finite. In other words, the hidden state is a fixed size vector, meaning it can only store a limited amount of information. Imagine that memory as a piece of paper. If you only need to write down a short sentence with 5 words, there's plenty of space to capture all the details. But as a sentence grows longer, 50 words, 100 words, you quickly run out of room. You might try squeezing in more information by writing smaller, overlapping words, or even raising some details to make space for new ones. At a certain point, what's written on the paper becomes unreadable. The same thing happens in an RNN. As the sequence length increases, older information fades, and the model struggles to retain all the key details. This leads to ineffective predictions, as the memory vector only holds a distorted or incomplete version of the original sentence. This limitation led to the development of long short-term memory, LSTM, networks. The idea is simple. We want to have more control over that memory and manipulate it accordingly, effectively using this limited memory to convey the most information. We will use the images from the video that Brandon Roher has made because I couldn't find a better way to convey the ideas behind the LSTM intuitively. This is his image description of the recurrent neural network. First, LSTMs introduce a linear layer called forgetting, which outputs a gating vector. This vector performs LMI's multiplication with the memory vector to determine what to keep or discard from memory. For example, if the memory vector is 0.8, 0.8, and 0.8, and the gating vector is 1, 0.5, 0, the result is 0.8, 0.4, and 0, meaning strongly remember the first 0.8, partially forget the second 0.8, and completely discard the last 0.8. This is like erasing unnecessary words from a page. Next, LSTMs introduce a linear layer called selection, which also outputs a gating vector. Its purpose is to filter what parts of the memory is passed to the next layers, ensuring only relevant information is used for the current time steps predictions. At last, LSTMs introduce a linear layer called ignoring, which also outputs a gating vector, and its purpose is to filter what parts of the current output goes into the memory, so the memory only remembers the essential information of the current output. Now, if you're wondering, wait, but what is the long-term memory and what is the short-term memory? Well, the predictions are the short-term memory, while the memory that we've been discussing so far is a long-term memory. This is how an LSTM is more commonly illustrated, and I'll slap the words on there over the intuitive parts I've just mentioned. Next, we'll have to understand about a certain application of the LSTM architecture, seek-to-seek, sequence-to-sequence, translating one sequence of words into another, whether that be translation or question answering. Seek-to-seek follows an encoder-decoder framework. As you see in this image, we get a source sentence, that is in Russian, and send it to the encoder, which processes it, and its memory constructs a representation of the sentence, which it passes to the decoder. The decoder is supposed to use this source representation to generate the target sequence of words. In this case, translating that Russian sentence into English, I saw a cat on the mat. The decoder doesn't just output a word directly. Instead, it generates a probability distribution over possible next words, considering both the encoder's memory and its own previous outputs. During training, we select the word with the highest probability as a predicted next token. However, in real-world use, we sample from the probability distribution to make predictions more dynamic. In TLDR, this image summarizes the process pretty well. As for training the network, at every time step of the decoder's outputs, we compare its probability distribution output to the real output, which is just a one-hot vector, and use cross-entropy loss to backpropagate. But LSTMs are still far from perfect. One major limitation is that the data must be processed sequentially, meaning each new input must wait for the previous one to update the memory. In training, we usually let the network simultaneously process multiple input feature pairs and perform stochastic gradient descent, but in the case of language, input and output sequences can have varying lengths, which makes parallel processing on GPUs highly inefficient. Another challenge arises with backpropagation and gradient descent. In a standard neural network, gradients propagate directly backward, but in an RNN, our network's outputs isn't just dependent on the current parameters with the current input, but also the memory. And what makes up this memory? It is a cumulative effort of all previous time steps inputs that have propagated through the network. This means that the gradient computation at any given time step involves contributions from an increasingly long history of how past inputs combined with the current parameters have altered the memory, and hence alter the output. But perhaps the most fundamental issue is still the memory bottleneck. While LSTMs attempt to optimize how memory is utilized, the hidden state remains fixed in size regardless of input lengths. This still creates the major limitation in transferring information from the encoder to the decoder. Now we finally introduce attention, a key breakthrough that addresses the memory bottlenecks in LSTMs. Instead of cramming the entire input into a fixed size memory vector, what if the decoder could see all parts of the encoder sequence and ask the question, what part of the encode sequence should we focus on to generate the next word in the output sequence? Let's just let this animation play here for a bit, since it's incredibly fancy for intuition, but we gotta explain what's happening at each step. First, we compute the attention scores between the current decoder state and all encoder states. These scores are supposed to indicate how relevant each input word is to predicting the next output word. An encoder state is just the output of the encoder at a time step, and a decoder state is similar, except it's not the final output. The attention scores are passed through a softmax function, converting them into a probability distribution, representing how important each encoder state is for the current decoder state. The attention weights, softmax outputs, are multiplied with their respective encoder states and summed up to form the attention vector, which replaces a memory vector used in traditional LSTMs, and the rest goes about the same as how a memory vector works. This image summarizes the process of attention pretty well, so I'll pause for a bit and let you read it through. The main idea of attention is that the decoder can have access to all the contextual information in the encoder and learn which parts of the context are most important at each time step, calculating the attention vector between the current decoder state and all the encoder states. So our encoder communicates with the decoder via attention now and not by passing through some memory. To wrap up today's note, let's talk about how attention is actually computed. Everyone's least favorite part, the math. There are multiple methods, but the most commonly used one is the dot product attention. Older methods like long attention are less relevant today. The dot product is a fundamental operation in linear algebra. For our purpose, it can be understood as measuring similarity between two vectors. If two word embeddings, the high-dimensional vector representation words, are generally pointing in a similar direction, the dot product will be large and positive, meaning they're highly related. If two word embeddings are pointing in different directions, the dot product will be small or negative, meaning they are less related. Now, as you can see from this image, computing the dot product isn't hard. We multiply corresponding elements of two vectors and then sum the results to get the dot product value. This is exactly how we do it for the attention score between a word and another word. A way to rewrite this operation can be as a vector multiplying by the other vector's transpose. It is the same operation written in a different notation, which helps us to quickly do the next thing, calculating the attention scores from a word to every word in a sentence. It works very similar to the word-to-word attention case, but a sentence can be seen as a matrix of multiple word embeddings, where each word embedding is a column of the matrix, and a quick way to compute the attention scores from a word to every word in the sentence is just by letting the word vector multiply the matrix's transpose. As that gives us a result the same as if we took the dot product between that word to every word in the sentence respectively, just faster computation. How about we take this a step further, the attention between a sentence and a sentence, basically calculating the attention scores from every word of a sentence to every other word in another sentence. Well, it's the exact same thing. We simply just multiplied the word embedding matrix 1 with the word embedding matrix 2 transposed. And ta-da, it's the attention scores between all the words of sentence 1 to all the words in sentence 2. This image is a sentence doing attention with itself, but you get the idea. You'll realize computing attention is a very fast process that can be done with all the data going to the network in parallel. So right now, our only part in the network that needs the data to be processed sequentially is that short-term memory. What if we can somehow get rid of this as well? Though that's thoughts for another day. In the next video, we will dive into transformers, the architecture that made up GPT, the iterative improvements of the GPT model, and explore how they revolutionized natural language processing.